purpose of the lambdas, the ability to define small strategy objects on the spot that can then be passed to methods that use them. Like, for example, define a small comparator on the spot that is then passed to the sorting function from the standard library. But let's see our next example of lambdas. So this one we're still not in the computation streams, and just to drive in the point that these lambdas can be used anywhere in the Java language, not just with the computation streams. So we do a little bit of black and white op art style graphics here with 6 different images. And all these images are created by one and the same method that receives a by predicate. So by predicate is like a predicate, but receives 2 arguments instead of 1. So by predicate of integers that receives the x and y coordinate of the pixel inside the image, and then tells with the return value whether the pixel should be black or white. So now, as a challenge, try to think of a formula for the pixel coordinates x and y, that when the formula, the truth value predicate formula, is applied for all the pixels of the image, produces a checkerboard or this kind of anti-diagonals, or this kind of nested circles, or this kind of interference pattern. So that's another, but it's not the most important thing in this example, that particular math. But then at least there is some image stuff for everybody. So let's read through the image loops class. So one static method compute image. Tell it the dimensions, the width and the height of the image that you want in pixels, and then the by predicate. So by predicate is one of these new concepts from the Java util function. So by predicate from integers to integers. So by predicate for 2 integer arguments, not the by function or something. So then an arbitrary predicate, and then inside the method, so we start by creating the buffered image. So buffered image is the concrete image subclass, the 2D pixel image that gives us the set RGB and get RGB, the ability to read and write the value of an individual pixel. So the buffered image, when it's created, all the pixels are black. So the 0 bytes that every object is initially filled in. So when interpreted as RGB colors, they are the black color. And then this method simply loops through the rows and the columns, so all the possible XY combos of the pixel coordinates in the image, and the pred. So here now that we receive the pred, so we cannot just, it would be nice like in Python we would just say pred, like the pred is the function itself in Python, but in Java pred is an object that contains the function, so therefore we have to call the actual function through the object itself. So if the Del Monte man says yes again, so that means that the pixel is gonna be painted white. So now think up for all these 6 images. So what is the code for the predicate that when applied to individually to the pixels of the image produces this particular pattern? So the main method, all the work is done. So we could have had this image panel as a separate inner class, but since we're only using it in the main method, so push all the way as a local class. So the frame contains an image panel, and I think it would be prettier if each image panel displayed a separate image the way that I had in the turtle demo. So now I have one image panel, and I have to calculate the positions of these images myself, so I'm not still doing this the best way. But so one day these examples will be perfect, but not today. So image panel is that entire thing that we display. So it consists of an array of images, and then in the constructor, so we create all 6 by calling compute image. So each one, the width and the height is gonna be 200. But then, so here extracted as a separate line for readability. So remember, white spaces don't matter. So, but just so that it's clear. So each one of these, so we create the by predicate strategy object from two integer values. So lambda expression. So if the method receives other than 1, so 0 or 2 or more, then the parentheses are necessary. If you wanted the lambda expression that takes no parameters, so that would be the empty parentheses, but this one takes 2. Notice you don't need to give the parameter types because the compiler knows it, because compute image expects a by predicate of integer and integer, so therefore it knows from that one that these are integer and integer. Well, they're gonna get the unboxed into primitive ints. So now, so what is the logic to make a checkerboard? So if you wanted to checkerboard where every square is 1 pixel, so you realize that is determined by the parity. So color with one color, if the parity of the x coordinate is different from the parity of the y coordinate, so that would make a checkerboard where every tile is 1 by 1. How can we make this 20 by 20 pixels? Well, just take the pixel coordinate and divide it by 20. So then all the pixels within the same 20 block are treated the same way. So so each the color is the parity, so if you go either right or down, you change the parity by 1 and therefore to the opposite color. How do we create this kind of diagonal stripes? Well, anti-diagonal actually. So what is the thing that all the coordinates in the same anti-diagonal have in common is the fact that their sum is constant. So if you're in an anti-diagonal, you go down 1 and left 1. So then you don't change the sum of your row and column number. So then again, so dividing by 20, otherwise the stripes are gonna be 1 pixel long. And now this is the parity of the sum of the x and y coordinate. So within the same anti-diagonal, because the sum never changes, so then all the pixels in the same anti-diagonal are colored the same way. A handy trick to know also. So this is, by the way, also as an aside, if you need to iterate through an infinite 2D quadrant, so the quadrant of the entire infinite plane. So you start at the origin and you need to loop through one by one all the possible pairs of xy coordinates arbitrary far until you find what you're looking for. So doing this in the anti-diagonal order. So the outer loop looping through the current sum of the row column number, so which anti-diagonal you're in, and then the inner loop loops through the possible row numbers, and then the column number for the row is always the sum minus the row number. So that one's handy to do like a iterative deepening search in a two-dimensional space. This kind of almost checkerboard, and here I've made it 15 by 15 for some reason, so that it's not matching exactly. So this one is now that both the x and y must have an even parity. Yeah, so then exactly 1/4 of the pixels have it. The same thing doing with the diagonals and anti-diagonals. And then the fifth one is interesting. So how do you recognize so this is now depending on the distance from the center, and it is the parity of what is known as the chessboard distance. So chessboard distance in the integer grid between two positions is the number of moves that a chess knight moving to one of the 8 pass chess king moves in a given number of steps. So from the center you calculate the chessboard distance from the center, and then the parity of the chessboard distance tells you whether the pixel is black or white. And again, so dividing by the pixel, the distance is by the width of the band, so that within the same band, so all pixels get the same result and therefore are the same color. And the last one, well, here we're doing some bitwise arithmetic here, so that's the topic for when we talk about the integers and doubles in Java. So bitwise arithmetic can create this kind of weird interference patterns.